All right, the purpose of this video is to help us see the mathematics behind the inferences on beta 1. So we'll get to, at the end of the day, or at the end of this video, we'll get to a point where we can do confidence intervals or the model utility test and just basically see the kind of things that we can say about beta 1. So I've got all the math written here. I'm just going to kind of walk through it so that you can understand it. I can post this as well if you guys want to see a copy, but most of it's straightforward, but we'll see what you guys think. All right, so we start off from the two videos ago that we can come up with whatever beta hat is based on this x transpose x inverse x transpose y. Given that that our matrix X looks like this, our Y matrix is a column vector, and then we can sort of multiply that out. Now, just for this particular video, I'm going to make my notation a little bit easier so I don't have this, because I'm only dealing with one predictor variable. I'm going to just let it be x1 be the superscript from our previous notation, just for this video. It's not that big a deal, but I'm using this notation so that I can have a second predictor and a third predictor. But for this lesson or for this video, I'm not really concerned with that. We just got a predictor variable and the response variable, and then beta with either beta hat or beta with the arrow, or I'm sorry, a vector symbol over there is beta 0 and beta 1. Okay. So x transpose x, if you were to take this thing and multiply, like basically take this matrix and actually this one and put it on its side, you would see you have ones on one column, or I'm sorry, one row, and then ones in column. If you multiplied all those suckers and added them up, you get n. If you did the same thing with a ones and the x1 to xn, you just get the summation of each one of these numbers, one of the predictor variables. You just sum all the suckers up. And you get the same thing. Obviously, x transpose x is a symmetric matrix, so whatever you get here, you're going to get here. But you could just do that multiplication. You can find out. And the last one would be basically taking this row times this column, right? So you would have x1 times x1 plus x2 times x2 and so on and so forth, and you get summation x squared. Okay, so that's x transpose x, and then x transpose y, same thing. Just take this matrix, set it on its side, multiply by that, and you get the summation of y sub I, so all these suckers together, and then the summation of that, that would be a row times that column, which would be that. Okay, so now if I want to take the inverse of a 2x2 matrix, we know how to do that. You just flip these and put negative signs on there over the determinant, so that's what you get here. And then the last thing I'm just doing over here is basically for beta 0, it's just this times this with that in the denominator, right? So that should be the denominator for both of them. So I get that in the denominator there, that denominator there, and then it's just this x1 squared times. I don't care about beta 0. I mean, you can do that multiplication yourself. But what I did here for the beta 1 is I'm saying n, because that's a positive number, just putting that one first. So n times this guy gives you this piece, and then minus, because there's a minus there, that times that gives you that piece. All right, so that's the numerator, and the denominator is just the guy in there. So the question is, how is this beta 1 hat? What is this distribution? Because really, that's what we need to know in order to be able to make inferences on beta 1 hat. What is the confidence interval of the true beta 1? Is beta 1 hat, is that is it telling us something? Is the relationship good, basically? So we want to be able to do a test on that. All right, so see if I can get this thing to work. All right, so scrolling down, what we do here is I'm just taking this and I'm bringing it over here, and so I'm going to do some things to this in order to be able to. I'm going to simplify it, do a couple things. So you can kind of see I just wrote it here. I multiply by 1 over n, which is just multiplying by 1. But then you multiply this thing, that n goes away, and you got an n on the denominator there, and you kind of keep going over. So I'm going to stay in yellow. Yellow is the numerator here for a second. So all I did was I made summation of x sub I and n to put all of that together. You get x bar, and then the summation. So the n goes away, and the summation of x sub I goes away. So we're just left with this, and then I can pull out a summation of x sub I, or y sub I, right? So I could basically take this x sub I minus x bar out, and then taking the y sub I out, and then summation sign on the outside of that. So you can see that this is what this thing simplifies to. This piece is a little bit stranger. It's probably easier to start here and go this way than it is to do what I did here. So I actually started here and went backwards in order to figure out the things that I had to add up in here, right? So if you've ever done this calculation before, it's called SXX. It's the sum of each one of your x of I. So it's sort of a, we've talked about this in the last video about it's sort of a variance of your x, right? So it's a measure of how far away each x of I is from x bar, right? So that's all that sucker is. And you can kind of see the math that kind of gets us there. Again, if you were to start here and go backwards, you would get to that one, right? So that's generally how people do this one. Okay, so all I'm going to do now is so B1 hat is equal to this thing in yellow. That's what went up there, and then divided by SXX, because we simplified this to SXX. So that's where we're going to start now. And all I'm going to do here is take the expected value, because I know these y sub i's are all, every one of my y's are distributed as a normal random variable. Well, how do I know that? Go back 2 videos ago, and what we're talking about is that epsilon that goes along with it. The epsilon piece was a normal 0 sigma squared, right? So if I add up all of those suckers plus some constant, whatever the constant is, that's also going to be a normal distribution. So I know y's are normally distributed, and if I add up a bunch of normals, we know that that's going to be a normal. So we know beta 1 hat is going to be some kind of normal distribution, but I want to know what the expected value is. So that's the first thing. So all I did here was brought it down, and I substituted in beta 0 plus beta 1 x of I in here, and then times that, and then just brought it in. So this times beta 0, so that's what you get here. You can bring the beta 0 out, and then you can bring the beta 1 out of the same sort of calculation. And note that if you sum up all your x of i's minus x bars, that's always going to be equal to 0. You can do that calculation. You've probably seen that before. And so that sucker goes away, this whole term goes away, and we're just left with beta 1 sum x of I squared, this whole thing here. So where did you get that from? We just bring it into the parenthesis, and then bring in your summation sign. So bring your summation here, and then you can bring an x bar out and get the summation of x of I. And then let's see, so turn this thing into summation of x of I over n. Summation of I is x over n would end up squaring that term, and then add that over n. And then what I just noted was the fact that that is the same. So these are exactly the same. And if I wanted to continue the process, I would get SXX on the top up here. So SXX over SXX cancels out, and we're just left with beta 1. So the idea here is, or the deal here is, the expected value of beta 1 hat is just beta 1. Bam, we're done with that. So I know that beta 1 hat is distributed as a normal distribution with expected value of beta 1. We don't know what beta 1, but that's what expected value is. Okay, the next part is I got to figure out the variance. And so if you remember variance rules, when you pull out a constant, you square it. If the variance of a constant is always going to be 0. I mean, there's lots of different rules. I think the only one we got to remember here is when I pull out a constant that we squared. So let's start, and that it's a linear operator. So we're going to start with the variance of this entire thing. So all I did was I took this guy right here and just started writing it out, right? So so I is equal to 1, you get x1 minus x bar, y1. x2 minus x bar, y2, and so on and so forth. And then obviously the denominator stays the same. And now I can bring in, so I have an SXX in each one of these, so I just pull it out of it. And so that's why I squared it. So 1 squared is just 1, SXX squared, and then the variance of this entire thing here. And then I can bring the variance inside again and pull out the constant. So this is a constant because it's that the y's are my only random variable. When I pull it out, I square it, and then I'm left with variance of y1, variance of y2, variance of yn. All of these are sigma squares, and I got x1 minus x bar, x2 minus x bar, xn minus x bar, all of those quantities squared. So I'm going to pull out a sigma squared of each one of those pieces. And that comes out, so it's not coming out of a variance, but it's coming out of this this thing that we've already taken the variance, and so we don't have to square the variance. So you just basically use an algebra now. So bring it out the squared, And then I have all of these x1s, x sub I is minus x bar quantity squared. And then we note again that that's just sxx. And when you divide these two, you're just left with sigma squared. And remember what sigma squared is, right? So sigma squared is the variance. So that's still how much the model, how much random error. It's that same sigma squared that we talked about in the first, I forget which video was that. Maybe it was the last video. But we were trying to figure out like how much the model, how much randomness was in the model. And that's what we're talking about here, right? So this is just that randomness that's in the model, and then these sxx, these cancel out, and you're just left with this. Okay, so the deal here is, or the distribution thing that I'm looking for is beta 1 hat is distributed as a normal distribution. Its expected value is beta 1, right? So that's pretty neat that we would expect to get the actual true parameter value, and sigma squared over sxx would be my variance. So if we take that and just, if we know that that's how it's distributed, now I can start doing things with it. So I can take my beta 1 hat, whatever that is, subtract beta 1, divide by the square root of sigma squared over sxx, and we know that's a normal 0, 1. And oh, by the way, we can now substitute in the estimate. So this S here is the estimate for, so it's sigma hat. So S equals sigma hat that we've already talked about, where we use SSE divided by n minus 2. So that's the S estimate, or the estimate for my randomness in the model. I'm going to divide by the square root of, and that's going to be a t to n minus 2. So n minus 2 so this is a new distribution that we haven't talked about maybe in this class, but I'm sure all of you guys are 376 is a prereq for the class, so you guys know what a t distribution is, and n minus 2 is the number, or the degrees of freedom of it. And why is it n minus 2? Well, I've used the data already to estimate two things. I've used the data to estimate beta 1 hat, and I've used the data to estimate S, so we have 2 less degrees of freedom than what we would have otherwise. All right, so this thing that I kind of circled in red here is really what we're going to use. And so let's go ahead and do a couple things. So again, I'm not going to bore you with how to calculate a confidence interval unless you guys really want to talk about it. We can definitely put it in a probability statement and come back and figure this out. But beta 1 hat is going to be plus or minus a t with alpha over 2, whatever your alpha is, whatever your level of confidence that you're interested in, n minus 2, this t distribution with an alpha over 2 as the probability in the tail. N minus 2 is your degrees of freedom. And then at this S beta 1 hat is just what we just talked about, this thing that's on the bottom down here. So if you do that, then you can get a plus or minus, you can get a confidence interval for beta 1 with the true value of beta 1. Again, remember what confidence interval is. Go back and check those out. Check out the wording on it. You know, it's if you did this 100 times, 95 times, you'd capture the true value of beta 1. Okay, and the next one is the model utility test. And let me kind of put this. So this is sort of a special hypothesis test where you set your H naught is beta 1 equals 0. So you're assuming your null hypothesis is that that your slope, if you will, of your, you know, so remember beta 0 is sort of the y-intercept, and beta 1 is really the slope, and that's the part that you're capturing with the x's, your predictors, right? So as your predictors move to the right, you're either going up or down based on what that slope is. And so what you're saying is, well, my null hypothesis is that it's 0. I'm going to have to produce some kind of evidence that that it's not equal to 0. So that's the idea behind the model utility test. And if you remember what a p-value is the probability of getting this kind of data with this relationship, given that H naught is true, would be, so what you're looking for is a small p-value. So small p-value is more evidence that this one is true, your alternate hypothesis. It's just giving you more evidence. So when you're looking at that, you can tell that. So, and I wrote it in a probability statement. So the probability of having this relationship between the predictor and response, or even more, given that H naught is true, right? So that's the idea. So what is that? What does that look like? What is that probability? Let's see here. So that would be, I'm sorry, your test statistics. So what would the what would the test statistic look like in that particular case? You would just be simply, let's see, beta 1 hat divided by S. I think that's how it is. S beta 1 hat. So that would be my test statistic if I was going to look at that. Why is that the test statistic? Remember, we're assuming H naught is true, right? So if you assume, so remember what well, let's go back up here. Let's just start here. So let's remember what the thing that I can't get it on the same screen here. So let me use that. Matter of fact, I'm going to delete this. I'm going to start up here. So let's delete. We're going to come up here and we're going to say beta 1 hat minus beta 1 all divided by S over the square root of SXX. That's a t distribution, and so we're assuming H naught is true. So what do I mean by that? Well, that guy's 0. So therefore, beta 1 hat minus 0, so I don't have to put that over here. This guy is just that S beta 1 hat, right? And what we're trying to do is, this is my test statistic. We can call it T. And then what we want to do is we want to calculate, because we're saying it's not equal to 0, and we know the T kind of looks like this, depending on what the number of degrees of freedom is. That's at 0. And then what you're doing is you're calculating the area in there, and the area in there, where this is that T statistic. So it goes up in here, and it goes negative T. So negative T and positive T. So this would be whatever these two things add up to be. Again, we would find these given, and we'll do it in Python here in class. We'll find some p-values given whatever our test statistics are for this model utility test. Anyway, I wanted to show you guys that just to make sure that everybody's on the same sheet of music before we start class. And we may or may not get to this next class, but we'll definitely get to in the next couple of classes, just so we understand what these tests are and the statistics that's involved in them. Okay, well, I hope you got something out of this one. I will see you next time.